Quantum mechanics isn't just a part of physics, it's the framework that underpins our understanding of the microscopic world. This field of science, both beautiful and bizarre, challenges our classical views of reality. At its core, quantum mechanics deals with the behavior of particles at the smallest scales imaginable. Here, the usual laws of physics cease to operate as we know them, and new, often counterintuitive rules take their place. Scientists like Max Planck, Albert Einstein, and Niels Bohr began noticing anomalies in experiments that classical physics couldn't explain. This led to the development of a new theoretical framework, which not only addressed these anomalies but also opened up a whole new realm of technological possibilities. It's a domain where particles can exist in multiple states simultaneously, behave both as particles and waves, and influence each other instantaneously over vast distances. This essay aims to demystify some of its core concepts, illustrating not only their scientific importance but also their practical applications in everyday technology. The concept of a quantum state is fundamental to understanding quantum mechanics. A quantum state represents the state of a system at a quantum level, encapsulating information about all possible states of a particle. Unlike classical states, which are definitive and observable, quantum states are described by probabilities. A particle in quantum mechanics doesn't have a specific location or velocity until it's measured. Before measurement, it exists in a superposition of all possible states. This probabilistic nature of quantum states leads to some mind-bending implications. For instance, until a particle is observed, it can simultaneously exist in multiple places or states. Mathematically, quantum states are described using wave functions. When a measurement is made, this wave function collapses to a specific state, which is the result observed by the experimenter. Understanding this concept is essential for anyone looking to grasp the basics of quantum mechanics. One of the most fascinating and revolutionary ideas in quantum mechanics is the wave-particle duality. This principle asserts that every particle or quantic entity may be partly described in terms not only of particles but also of waves. It tells us that the behavior of microscopic particles, like electrons and photons, can exhibit characteristics of both particles and waves. In classical physics, waves and particles are seen as distinct entities. A particle is a discrete packet of matter, while a wave is a continuous oscillation through space. However, in quantum mechanics, entities like electrons can behave like particles when they hit a screen, but like waves when they pass through a slit and create an interference pattern. The classic demonstration of wave-particle duality is again the double-slit experiment. When light, or any matter, passes through two close slits, it creates bands of light and dark on a screen, a pattern indicative of wave interference. Understanding wave-particle duality is essential for grasping how quantum mechanics differs fundamentally from classical physics. The uncertainty principle, formulated by Werner Heisenberg, is a key pillar of quantum mechanics. This principle states that it is impossible to simultaneously know both the position and the velocity of a particle with absolute precision. The more accurately we know one of these values, the less accurately we can know the other. This is not due to imperfections in measurement or technology, but a fundamental property of the universe at the quantum level. This indeterminism is a radical departure from the deterministic ideas of classical physics, where the state of a system at one time determines its state at any future time. In the quantum world, however, even with complete knowledge of a system's wave function, we can only predict probabilities. The uncertainty principle has profound philosophical implications, challenging the classical notion that the universe is a clockwork mechanism with predictable outcomes. Despite its implications, the uncertainty principle has been confirmed by countless experiments and has become a cornerstone in our understanding of quantum systems. Quantum entanglement is one of the most intriguing and mysterious aspects of quantum mechanics. Albert Einstein famously referred to it as spooky action at a distance. When particles become entangled, the state of one particle cannot be described independently of the state of the other, no matter the distance separating them. This connection persists even if the entangled particles are light years apart. If two particles are entangled, measuring a property, like spin or polarization, of one particle instantly sets the corresponding property of the other particle, regardless of the distance between them. This instantaneous transfer of information seems to defy the speed of light limit set by Einstein's theory of relativity. Entanglement has been demonstrated repeatedly through experiments. most notably in Bell's theorem experiments, which show that the results cannot be explained by any theory based on local realism. Furthermore, quantum entanglement is at the heart of emerging technologies like quantum computing and quantum cryptography. Understanding entanglement is not only crucial for physics, but also for the future of technology. Lasers, an acronym for light amplification by stimulated emission of radiation, are a practical application of quantum mechanics that have revolutionized multiple fields. The functioning of lasers relies on the principles of quantum mechanics, particularly those involving the energy states of electrons. In simple terms, lasers work by exciting atoms to a higher energy state. When these atoms return to a lower energy state, they emit photons. By stimulating these emissions, lasers produce a coherent beam of light with many practical uses. From the checkout lines at grocery stores to cutting-edge surgical procedures, lasers have become an integral part of modern life. In telecommunications, lasers transmit vast amounts of data over fiber optic cables. In medicine, they perform precise surgical cuts and destroy tumors without damaging the surrounding tissue. The development of lasers is a testament to the practical power of quantum mechanics. Transistors are another groundbreaking technology that owes its existence to the principles of quantum mechanics. These tiny devices are the building blocks of all modern electronic circuits, including computers, smartphones, and virtually all other types of digital devices. The operation of transistors is based on the quantum behavior of electrons in semiconductors, materials whose electrical properties can be altered by adding impurities, a process known as doping. The ability of transistors to act as switches and amplifiers is central to digital computing. By controlling the flow of electrons through a semiconductor material, transistors can turn electrical signals on and off. This binary functionality is what allows computers to perform complex calculations at incredible speeds. Without transistors, the digital age as we know it would not exist. Quantum mechanics plays a critical role in the design and function of transistors. The impact of transistors on society has been profound, enabling the development of technologies ranging from portable radios in the 1950s to the powerful and ubiquitous smartphones of today. Nuclear energy, which currently powers millions of homes and facilities around the world, is another application of quantum mechanics. At the heart of nuclear energy is the process of nuclear fission, where the nuclei of atoms are split into smaller parts, releasing a tremendous amount of energy. This process is governed by the principles of quantum mechanics, particularly those pertaining to nuclear forces and decay probabilities. The operation of a nuclear reactor, which is the most common method of generating nuclear energy, relies on a controlled chain reaction of nuclear fission events. By manipulating the conditions under which these reactions occur, scientists can harness the energy released as heat and convert it to electrical energy via turbines and generators. Nuclear energy provides a significant portion of the world's electricity supply and offers a low-carbon alternative to fossil fuels. However, it also comes with challenges such as radioactive waste disposal, safety concerns, and the potential for catastrophic accidents. The role of quantum mechanics in nuclear energy is a powerful example of how deeply theoretical physics can impact society and the environment. The influence of quantum mechanics on modern technology is profound and all-encompassing. This branch of physics, which began as a theoretical endeavor to explain the behavior of matter at the smallest scales, has led to technologies that have reshaped our world. From the lasers and transistors discussed earlier to MRI machines in hospitals, quantum mechanics has been a crucial element in numerous technological breakthroughs. These technologies not only demonstrate the practical applications of quantum principles but also highlight the unexpected ways in which scientific research can lead to real-world applications. Looking to the future, the ongoing developments in quantum computing and quantum cryptography promise to revolutionize fields such as cybersecurity, drug discovery, and optimization problems. These technologies leverage the unique properties of quantum mechanics, such as superposition and entanglement, to perform tasks that are beyond the reach of classical computers. The story of quantum mechanics is a testament to the curiosity of the human spirit and its relentless pursuit of knowledge. Quantum mechanics is not just a chapter in physics, it's a framework that has expanded our view of the universe. Through its strange and often counterintuitive principles, It has challenged our classical understanding of reality, unveiling a world that operates very differently at the microscopic level. The exploration of quantum mechanics is a journey into the very building blocks of nature, revealing how particles come together to form the vast universe we inhabit. The implications of quantum mechanics extend beyond the scientific community, influencing philosophy, technology, and our general worldview. It compels us to reconsider what we know about the nature of reality and our place within it. As we continue to unravel the mysteries of quantum mechanics, we not only unlock the secrets of the universe, but also pave the way for future generations to innovate and explore. Understanding quantum mechanics is crucial for anyone interested in the frontiers of science and technology.